First speaker is Shamindra Ghosh, and he will be speaking on affine representations of planar algebra.
Thank you. Thank you, Vijay, and thanks to Sundar for being such a superb advisor. I have already told stories about Sundar yesterday, and I don't want to repeat again, but just wanted to say happy birthday, and we look forward to the next 60 years. Okay, so planar algebras is something which I started working on with Sundar. He is the one who introduced all these things to me. And today I will be talking about affine representations of planar algebra. And this is a project, not a project. This is probably the most general version of my thesis work, which we have been able to do with Paramita and Ved last year. So let me give you the brief background. It's quite technical to go to describe what a planar algebra is, what affine representations of our planar algebras are. But if you treat planar algebras and representations as black boxes, so this is what we have done so far. So subfactors is the main thing from which planar algebras came. So n in M is a subfactor, means 2 on factor n and 2 on factor m, unital inclusion of subfactors. And as in any subject of any branch of mathematics, there is an ongoing classification program of subfactors going on. And in order to classify subfactors, you need invariants. And we will talk about a particular invariant, which is given by Vaughan Jones, the planar algebra, in 98. And after giving planar algebras, he worked on representations of planar algebras, that means actions of these planar algebras on Hilbert spaces in particular. And the reason was how he could produce new subfactors. So planar algebras are invariants of subfactors. So from these invariants, these are like typically pictures on the plane. So from these invariants, how can you produce subfactors? So this was the main goal for Jones, to look at the representation theory of planar algebras or action of planar algebras on Hilbert spaces. And we will denote this Hilbert affine p modules as HAPM, and this was introduced by Vaughan Jones in 2001, and it is an additive category. You can take direct sums and so on. So, and let me shift to a different topic, Dreamful center, which was happening in category theory. So what is Dreamful center? You have a tensor category C, so objects and morphisms, and you can fuse two objects and so on. Dreamful has this construction of center construction of the category C, and which we denote by ZC, which is a braided tensor category. So objects, if you fuse two objects, that is not the same, but it is naturally isomorphic to the opposite tensor if you flip the tensor. So given a tensor category, one can produce its center, which is another category, which is a braided tensor category. For example, if we take a finite dimensional Hopf algebra, there is a construction of quantum double. So double of the Hopf algebra, which is defined in this way: dH is the double of H, and you take the tensor product of actually a dual of H and H itself, and op here means the algebra in H, it is just the opposite algebra, and dH turns out to be another Hopf algebra, you can have this algebra structure and co-algebra structure and so on. It's a nice Hopf algebra. Then it's a standard fact that the representation category of the quantum double of the Hopf algebra is actually equivalent to the center of the representation category of the Hopf algebra. Actually contravariantly equivalent, there is, it's not actual equivalence. So how are these affine representation or affine modules linked with the Dreamful center? Okay. Let me briefly go over my thesis now in 2003 under Sundar. So I had no idea that there was any link in this. I just was looking at certain kinds of subfactors, very simple kinds of subfactor coming from finite groups, and we were like myself and Sundar, we were trying to find affine modules over these simple subfactors, group theory coming from groups. So and that will show you that like how they are linked, affine modules and Dreamful center. So suppose you take an outer action of a group, finite group on a 2 1 factor, so G to aught M, and outer means that G none of the element except the identity is a conjugation by unitary of M. So M is a 2 1 factor, by the way. And once you have this outer action, you can construct a subfactor by taking M as the big one and the smaller one as the fixed point subfactor, the elements which are fixed by all group elements of G. Okay. And this is a nice subfactor and it has index the cardinality of the group. And from this, if you take the planar algebra P and then you take the representation category of this planar algebra, like affine Hilbert affine P modules on this planar algebra, then what in my thesis what I have shown is this is equivalent to the representation category of the quantum double. Okay. And as I showed in the previous slide that quantum double, representation category of quantum double is again equivalent to representation category of the group, okay, because the group algebra forms a Hopf algebra, right. So it turns out that the Hilbert affine P modules of this particular subfactor is actually equivalent to the center of the representation category of the group. And let me rephrase this this theorem of my thesis in another form. It is a standard fact that for this particular subfactor, if you consider the NN bimodules, not all NN bimodules, but those which are generated by this canonical bimodule, NN bimodule given by L to M NN. So M is the bigger factor, so it can be used, it can be seen as a bimodule over NN. So you take the tensor products of L to M NN and they take the contragradients and take all the submodules on this higher tensor powers, and that will form a tensor category. Let's call that CNN, okay, the NN bimodule category. And it's a standard fact, if you take this subfactor, this particular subfactor, then this bimodule category is equivalent to the representation category of the group. So you can just replace this representation category by the center of the you can replace this representation category by the bimodule category. So this is what we have. Now looking at this result, as well as another conjecture in the world of TQFTs by Kevin Walker, Vaughan Jones, what he conjectured was, given any subfactor not coming from finite groups, any subfactor but having finite depth, okay, I will tell you what finite depth is, and if you have a planar, if P is the associated planar algebra, then the Hilbert affine P module is actually equivalent to the center of the NN bimodule category. That NN bimodule category which I talked about, this is the same, it can be defined for any subfactor. And what does finite depth mean? Finite depth means that the irreducible NN bimodules, the number of irreducible NN bimodules are finite if you consider up to the NN bimodule isomorphisms. So, this was the conjecture, and this conjecture made only sense for additive category, like just an equivalence which preserves direct sum. There was no tensor product. See, the center is a braided tensor category, but for affine modules there was no tensor product. Actually, that was another question of one, that how can you fuse two affine modules. So, in any case, in the beginning I actually never believed that this is true, and it was only last year with Paramita and Ved we were looking into generalizing this result of mine from the group case to the Hopf algebra case. So, we showed in January, we showed that the conjecture is indeed true if you take irreducible depth 2 subfactors. Okay. Irreducible depth 2 subfactors are basically those subfactors where which comes from the minimal action of finite dimensional Katz algebra. It is just a little bit of generalization from the group case. Okay. So, but then what we did is instead of irreducible depth 2, so without the irreducibility whether it works. Okay. So, we went to Paramita's thesis and we were trying to play around with the pictures, and it was really nasty calculation, and it turns out that even without irreducibility the conjecture is true. But now you see that if without irreducibility, that means any weak Hopf algebra, if the conjecture is true, it should be true for any depth. The reason is any finite depth can be like seen as a intermediate subfactor of depth 2. Okay. So, the NN bimodules generated in that will be the same. So, this should be true for any finite depth, but the calculations were really nasty. So, we actually put that aside and we had a fresh look, and it seems that what we could prove is not just finite depth, we could prove for infinite depth that this conjecture is true, but in the infinite depth case. So, infinite depth means the isomorphism class of the NN bimodules could be infinite. So, in the infinite depth case you have to put some extra finiteness criteria in the Hilbert affine P module. Okay. Otherwise, it is not true, which comes for free if you take the finite depth case. So, the conjecture holds, conjecture is true, but in the infinite depth case you have to modify if you want to establish the equivalence. So, Ved will talk about this conjecture, but this talk I will give you tensor product, contragradients, braidings on Hilbert affine P modules, okay, and the analytical aspect of this. Okay. The braided tensor category captures a very finite core of the representation category of the planar algebra, but once you go out of this finiteness criteria, that is where you will see the analytical properties of the planar algebra. So, we will talk about all these things. So, this was the background. Now, so what are planar algebras, what are affine representations? So, this is the main thing. So, I have to define what a planar algebra is. The building blocks are planar tangles. So, what is a planar tangle? You have an external disk, this is just an example of a planar tangle, and then you have internal disk. Inside the external disk is D0, D1, D2, D3, and it might be possible that a particular tangle might not have any internal disk at all. Okay. And then you have even number of marked points on the boundary, for example D0, I mean external as well as internal. So, this has 6 boundary points and D0 has 8 boundary points and D3 has no boundary points. So, even number of points in the boundary. Then you have strings. Okay. So, you attach all these marked points by strings, okay, and you can have a string just hanging out there with no endpoints. So either a string will have 2 endpoints or the string will have no endpoints. And moreover, you will have a checkerboard shading like this, and there are basically, given a tangle, you have 2 kinds of shading, and the shading is a part of the data of the tangle. And now once you have a shading, these numbering becomes irrelevant, because for example, the numbering is done clockwise on each disk, and what you can do is, between the last and the first point, if you put a sign plus or minus depending upon it is shaded or unshaded, then you can recover the numbering going clockwise. Okay. So you can, for example, you look at D2, so between 1 and 6 it is shaded, so you will put a minus there, right. And for example, for D1 between 2 and 1 going clockwise, you will put a plus there, and so on. And D3 will have only minus, because it has it is in a shaded region, and there is no shaded means it's minus and unshaded means it's plus. Now, and you also have planar isotopy. Planar isotopy means you can this is on a plane, and you can take isotopy which so basically the things are elastic, you can move around freely, but without making any crossings. So it cannot be non-planar, it has to be planar. And such a tangle you will think as, you will have multiple inputs and one output, and the input and output will be labeled by signed non-negative integers. For example, D1 has 2 points, so for that we will assign a color. Color will be a signed number which is +1, half the number of boundaries and this sign. Okay, D2 will have color -3 and D3 will have color -0, and this tangle actually goes from this input to this output. This is just a representation how a tangle will look like, I mean how we will refer a tangle as. So once we have a tangle, okay, so here one thing, for it might so happen that the tangle might not have any internal disk. For example, this is an example of a tangle where there are no internal disks. Okay. And then we have composition of tangles. So you can compose this tangle T and S, not everywhere. In D1 you cannot compose because there are only 2 points in the boundary and it has 6 points, but in D2 you can compose. So what you do is you like increase or decrease, or you shrink or stretch S in such a way and put it inside D2. In such a way this the distinguished boundary component which are marked by a sign, they should match, right. And then you just erase the boundary and erase D2. So this is the composed tangle, and the composition is done over the disk D2 of T, and you have put S inside, and then the input becomes reduced, like number of inputs is just 2, D1 and D3. So +1 going from +1 -0 to +4. Okay. So this is how you compose, and with respect to this composition you have identity, okay, identity tangle, and this is just the identity tangle of +2. So if you compose this tangle inside another, you just don't get anything new, okay, it's just joining everything to the internal disk. So this is the identity tangle. So now what is a planar algebra? So suppose the colors call this COL is the set of colors which is a signed number, positive integers, non-negative integer, I am sorry, and the planar algebra P consists of mainly 2 things. One is the space of a collection of vector spaces for each color, P epsilon k, for epsilon k belongs to col, and an action of tangles on these vector spaces. So what do I mean by that? That if T is a tangle which has input n many internal disks with colors epsilon 1 k1 to epsilon n kn going to output this epsilon 0 k0, then P sub T will be the action of T, and that will be a multilinear map of the vector spaces corresponding to the input colors to the vector space corresponding to the output color. Okay. But if you do not have any internal disk, it will be just an element of the vector space corresponding to the color. Let me illustrate in this example. Okay. And also the composition and identity should be preserved. So, what do I mean by that? So, T here is a tangle from +1 -3 -0 to +4. So, the action of T should be from P +1 cross P -3 to P -0 to P +4, and multilinear map, and S is a tangle without any internal disk. So, PS should be just an element of P -3, it should be P -3, I am sorry about that, this is a misprint, P -3, and the composition such that the action preserves composition. So, what do I mean by that? Now, let us compose T and S on D2, then the action of the composition is goes from P +1 cross P -0 to P +4. So, what we demand is action preserves composition means PT composed with like in the D2 input space, if you put this PS, then what you get is PT composed with S. So, this is just action preserving composition. Now, this is the most general definition of not most, this is the general definition of planar algebras. We need more adjectives to make this planar algebra correspond to a subfactor. So, what are the adjectives? The vector spaces of the planar algebra, they should be finite dimensional, and the zero spaces. So, the vector spaces are basically given by double sequence of vector spaces. So, at level 0 it should be one dimensional. Okay. So, that means P has modulus delta plus and delta minus. So, modulus means, so you have seen that here you have a loop which is not attached to any boundary. What you can do is you can erase this loop at the cost of multiplying a number which could be delta plus or delta minus depending upon the inside of the loop is shaded or unshaded. So, if the zero space is one dimensional, you have modulus, and then you have P has star structure, P has positivity, I do not want to go into these technical details, and then P is spherical. Spherical means that the tangle if you keep like spherically invariant. So, the action of tangle, if you put it on the sphere and if you turn things around the sphere, and the action does not change. So, that says that these two modulus, they should be the same. Now, a planar algebra satisfying all these conditions is called subfactor planar algebra, and what Vaughan Jones proved in his 1998 paper is starting from a finite index extremal subfactor. Extremal is some technical stuff. A finite index extremal subfactor, Vaughan Jones produced a subfactor planar algebra, and which is the invariant of a planar algebra, and from this subfactor planar algebra you can reconstruct a finite index extremal subfactor. The first thing was done by Popa and Jones, and then by Guione, Jones, Liaktenko, Walker, and Kodialam Sundar independently. So, there are various versions of reconstruction. Now, we will be working on these subfactor planar algebras. Let us go to now affine representations of these planar algebras. For that we need more definition. So, what is a P-labeled affine tangle? So, it is not a usual tangle. Here you must have at least one internal disk. So, here that demand of having at least one, we make that one to be a distinguished one and make it a red rectangle here, and you have an external rectangle like any tangle. So, I am defining affine tangle using this this example. So, P labeled affine tangle, P is the planar algebra. So, you have a rectangular annulus, and then you have internal disks like this one, this one and this one, and it might so happen that there are no internal disks. The internal disk has to be in the rectangular annulus, not inside the red rectangle, and you should have marked points in the boundary of the rectangular annulus and the internal disks, and you join these marked points with strings, and then you have a checkerboard shading, And then the most important thing is affine isotopy. So we are not allowed to stretch and shrink in whatever way we want. Here we are allowed to, we have the freedom of stretching and shrinking, keeping the boundary of the rectangular annulus fixed. For example, the inside of the inside rectangle you cannot move by 360 degree, and that will give you the same affine tangle. It will give you different affine tangle. So affine isotopy differs from planar isotopy as in tangles. And this affine p-labeled, what is the meaning of p-labeled? Now these internal disks, not the internal rectangle, will be labeled by elements of p. Okay. For example, this has color 4 points in the boundary and plus sign here, so it has color +2. So this will be labeled by an element of p +2, and this has color -1. So this will be labeled by an element of p -1, and such a picture will be called a p-labeled affine tangle up to affine isotopy, not just one picture. And let us call it A, and we will denote it, the input is +1 because there are 2 points in the boundary, which is 1, and there you have on the internal rectangle this is plus, and on the external rectangle we will put a sign here minus between the last and the first point going clockwise. If you have to put a minus sign here, and there are 4 points in the boundary. So A goes from +1 to -2, and you can compose two affine tangles but just by putting external rectangle of one affine tangle inside the internal rectangle of the other one. And there should be since there might be a problem with affine isotopy, because in affine isotopy you are not allowed to like change the boundary. So you have to do some technical stuff with the, like you have to inflate it. There should be one constant homeomorphism which will inflate the rectangular annulus and then again shrink it with that exactly inverse map of that. Okay, now I need to define. So this was an example of a p-labeled affine tangle. Another tangle is an unlabeled one, which is a very important unlabeled tangle. So here also you have rectangular annulus and you have stuff around the internal rectangle, and here what I have done is I have marked the strings with even numbers or odd numbers. So and that means that there are 2l many parallel strings here and 2k many parallel strings here, and you have m many parallel strings here, and you have an internal disk here which is unlabeled. Okay. So such a thing I will call it as psi super m epsilon k eta l. Epsilon k corresponds to the color of the internal rectangle and eta l corresponds to the color of the external rectangle. And the remark why this is important, because any p-labeled affine tangle A can be expressed as this unlabeled tangle acting on T, where T is any p-labeled planar tangle. So inside this one you put a tangle T and it will give back your A. So how is this done? So let us take the example which I was describing. So you have this affine tangle, but you have affine isotopy. So you can, stretching and shrinking is allowed, but inside the rectangle, keeping the rectangle fixed. So what you do is you bring everything very close by, this x and y, you bring everything very close and put it inside this T. Okay, and you have 4 points going in the top, because there are 4 points in the boundary of the external boundary, 2 points going down, and there is just one string going around the internal disk. And this is not a unique, there could be many representations of many T's, and this one can be 3 also. You can go around and come back, and you can wiggle the string around, and so this is not a unique representation. Nevertheless, it is very important for us. So for example, the T here is basically this picture which you see. So if you shrink this T and put it here, you will get exactly this affine tangle. Okay. So now what is an affine category over P? It will be denoted by AP, and the objects are plus or minus non-negative integers. and morphisms. So going from color epsilon k to eta l, so epsilon and eta are positive plus or minus, and k and l are non-negative integers. You take all p-labeled affine tangles going from epsilon k to eta l. So internal rectangle is epsilon k and external rectangle has color eta l, and take the linear span of this collection of pictures and mod it out by the relations coming from the planar algebra. So any affine tangle can be written as psi m epsilon k eta l of x. X is a linear combination of labeled tangles. Now p acts on these tangles. These are, x is a proper tangle or a linear combination of tangles. So p acts on these tangles, and if that action is 0, you set the affine tangle to be 0. Okay, and these will be called affine morphisms. And we can also compose, and there is an identity affine morphism, and also star of affine morphism is just reflecting an affine tangle inside out, okay, and replacing the labels by their stars, corresponding stars. Now what is a Hilbert affine p module? So these are the actual things which we worked on. So Hilbert affine p module again is a collection of Hilbert spaces for each color epsilon k, and each affine morphism will A go in the affine morphism space going from epsilon k to eta l. There is an action of A, V sub A, which is a bounded linear operator from V epsilon k to V eta l, such that it should preserve composition, identity, and the star, right, which means that if you V of A composed with B is V A composed with V B, and V of the identity is identity of the particular V epsilon k, and V A star is V A whole star. Okay. So it is like a star functor from the category AP to the category of Hilbert spaces. A trivial example will be the planar algebra P itself. If you take V epsilon k is P epsilon k, and if you take the action as the these affine tangles can also be viewed as like normal tangles, and it has an action on these the planar algebra vector spaces. So that will be the trivial example. Okay. Now how do we build all these Hilbert affine p modules? So we got just one trivial generic example of trivial affine p modules. To build, we have to look at the algebra AP epsilon k epsilon k. So it is an algebra because endomorphism space. So it was not even known that whether this algebra is a star algebra or can be made into a sister algebra after completion or not. So the first thing which we got is a faithful tracial state on this star algebra. So a typical element, and how is this defined? Let me tell you. A typical element of AP epsilon k looks like this, psi of that. So you have a label x coming from the planar algebra vector space P, and you have strings around the internal disk, and you want to send it to the complex numbers. So how do you do that? So what we do is we cut this string here and it becomes straight. So x, so this label has it looks like a crossing then, and what we do is we join the top and the bottom by this loop, as you can see 2k, and then there will be two free ends, and these two free ends what we stick some elements from the planar algebra. I will tell you what they are, and what in the end what you get is a zero tangle, because outside there are no internal disks. So you can put a like dummy internal disk external disk outside, and it will be an element of the zero space, and you know that a zero space in the subfactor case is complex number. So that is how the trace is defined. Oh, okay, yeah. Okay, so yeah, and then what we showed that these affine morphisms actually acts on itself, and the action is bounded, and these will give you regular Hilbert affine p modules. So from this you have two kinds of norm. One is the universal norm, which comes from taking supremum over so affine morphisms, norm on affine morphisms. You take norm of the action of this particular affine morphism with respect to different Hilbert spaces, and you take the soup norm, and that will give you a C star norm, and the reduced norm comes from this taking the L2 space corresponding to the trace which I just defined. So, the natural thing is the universal norm is greater than the reduced norm, and the reduced norm is actually greater than 0. So, it is non-trivial, and the universal norm is also finite. Okay. So, that we had proved, and we also have an estimate of the universal norm. So, it is natural to look for conditions on P when these things are equal. So, we are actually talking about amenability of planar algebras. So, G is a finitely generated, what we could prove in an example is, if we take a finitely generated group, there is something called diagonal planar algebra, and we could show that G is amenable if these two norms are same, if and only if. Okay. So, amenability we define, affine amenability we define as universal norm becoming same as reduced norm, and there is an amenability in the context of subfactors, so which was given by Popa. So, we could show that if a planar algebra is amenable, then the subfactor is amenable in the sense of Popa, but we do not know whether the converse is true. Also, there could be a definition of property T of subfactors. Okay. I just do not have time. Fusion, there are 3 things. I think I will leave it to Ved if he has time to talk about the fusion, and the time is over, right? Yeah, yeah. So, okay, so fusion was not there. Now, the reason why we wanted to do fusion is for property T, because property T basically philosophically it means that the trivial representation is isolated in the Feld in some kind of Feld topology, and here we have a trivial representation which comes from the planar algebra, but trivial in the sense that we can build it trivially, but not in the sense of fusion. So, trivial it should be in the sense of fusion. So, like having a proper fusion of these modules was important. So, that is what we did. So, we had fusion, we had contragradient of this, and we even have braiding, which was inspired by what we have this from the Dreamful center. But here we are talking about infinite dimensional, which might not, which could be non-trivial. So, we have this infinite non-semi-simple category, which is a braided tensor category, which could be fantastic to work on. Like you could like at least Von Jones was saying that if you take temporally leap, you might get the mapping class group. I am not very sure about that, but like we haven't worked on non-semi-simple categories where you have this, which is a very nice braided tensor category, and we can try to find invariance, and it could be useful. Okay, I will stop with that. How do I prove that it is strictly positive? Well, actually the positivity is the most non-trivial, but it is quite long. How do we prove? Oh yeah, okay, yeah, right, very good. So, in the 0 level it is a fusion category of the NN bimodule, and the fusion category is a star algebra. Fusion algebra is a star algebra, and if you send the trivial bimodule to 1, and that will give, and every other irreducible to 0, that is a faithful tracial state. Okay, so that is a baby case, but in the like higher level, KK level, it is a little bit more complicated, I would say.
So is there, so I'm not sure if I understood that, but is there a way, so the way I would sort of naively approach it is, right, sort of to write down a positive element in this thing and examine what these pictures look like in the planar algebra?
Yeah, in the end what we had is actually we worked with some subspace of the planar algebra, and there we knew something is positive map, and we could we use that. So in the end we had to work with the planar algebra. Otherwise there was nothing. I mean.
But it required some decomposition of the
No, actually it was quite explicit. You take suppose you take an affine morphism A star. We actually broke it. It could be seen as a map from the pk to complex number, and that map was positive definite. That's how we did.